I'm not going to go through all the derivation, but if you're interested, you can take a look in the book. But the basic idea is what we're using here is something called the thin lens approximation. Which says that if you have, it turns out that in this situation you have your converging lens, for example, the center axis. And let's say you have a light ray that's parallel to that center axis, some distance y, coming in a perpendicular distance y above the axis. And again, that's going to be bent. If it's parallel, it's going to be hit here, and that distance is the focal length. Well, if I look at this angle theta, let's call this angle theta, then we can just do the trigonometry and say that the tangent of that angle is that perpendicular distance y over the focal length, little f. But for thin lenses, what we're typically dealing with are situations where the angles are small. Okay, so this is kind of an exaggerated picture. What we're usually dealing with is something like this light ray comes in, and then this light ray is bent to something like that. And we have a small angle here. And you might know that if you're using, I draw this, so this is f now, this is y. Well, here's some distance, the hypotenuse of this triangle. This is a right triangle. This hypotenuse is some distance r. If this angle was small, then y over r is approximately equal to y over f. And y over r is the definition of the angle theta in radians. Okay, so if you measure theta in radians, by definition, it's this distance divided by the radius. So we can say that this is approximately just equal to the angle in radians. And then you have to go through some geometric arguments, which I'm not going to go into. But what happens is you find that any light ray is always going to be bent at the same angle. Okay, so if this is angle theta, but a light ray coming in from here, as long as it enters the same, or as long as it's the same distance y above the center axis, will be bent at the same angle. Okay, so that angle from, how do I want to draw this? The angle of deflection away from this original direction is the same angle. You can go through some trig and some geometry, and what it turns out is that based on that fact, based on the fact that the angle is equal to the perpendicular distance y divided by the focal length, you can work out what's called the thin lens formula. Which is 1 over the focal length is equal to 1 over d1 plus 1 over d2. Now, what's that mean? Well, f is the focal length. D1 is the distance from the center of the lens to the object, or to the source. Say the source or the object. And D2 is the distance from the center of the lens to the image. Okay. So if we apply this to, let's just try a quick example just to show you how this works. But if you have a focal length of, say, 12 centimeters, okay, and you have an object, so here's your focal length, f, and this is 12 centimeters, and you have an object that is a d1 of distance of, say, 18 centimeters away. Calculate, use this formula, plug it in. So what do you get for d2? So you have focal length of 12 centimeters, d1 is 18 centimeters. What do you get for d2? Where's the image going to form on the other side of the lens? (36 centimeters? Okay, so you have 1 over the focal length minus 1 over d2 gives you, or excuse me, 1 over d1 gives you 1 over d2. And so you have 1 over, I'll just keep it all in centimeters, 1 over 12 minus 1 over 18 is 1 over d2. And then you say d2 is 1 over all of that. And that gives you 36 centimeters. Okay. So somewhere 36 centimeters away, you're going to get a real image form that's inverted on this side of the lens. Okay. What if, same focal length, what if d1 is equal to 6 centimeters? So now the distance away to the object, from the object to the lens rather, is less than the focal length. So here's the object, here's the focal length. What are you going to get for d2? Work it out. Well, it should be pretty easy, right? What are you going to get? 1 over d2 is going to be equal to what? Negative, not negative 1/6, negative 1/12, right? Negative 1/12. So d2 is going to be equal to negative 12 centimeters. What's the negative mean? Not reflection, but what did we just talk about? If it's inside the focal length, you get not a real image, but a virtual image. So the negative here in this case means a virtual image. You're going to get an image that is apparently formed on the same side of the lens as the actual source, and that's where the negative sign comes in. So you have to be able to interpret the signs correctly. The same formula actually applies for diverging lenses. We won't go into the details here, but basically this is the formula about which most optics is built around. Okay, now if you get into sophisticated applications, you have to deal with non-thin approximations. You have to deal with things like chromatic aberration, where different colors might be refracted at different ways. But when you're constructing just basic optical equipment, this is sort of the formula that governs it all. Okay. If you need more details, you can certainly go and take a look in the book.